Okay, as mentioned earlier here, take a moment and try this out. What is the answers here? We got some thermodynamic equations. We're given the delta H, and give it a whirl. Pause the video, try it. Okay, so on this one, this is just one giant proportion. So if we have 895, now this is kilojoules per one cycle of the reaction. So that's 1 mole of this, 2 moles of that, gives me 1 mole of this and 2 moles of that. So I can really frame this energy in terms of any of these because they're all connected. 890 kilojoules, if how much of this is burned would be 1 mole, and that's 12 plus 4 is 16 grams. That's per, how many grams of this was 2 moles of that, which would be 2 moles, well, 1 mole of O2 is 32, so times 2 would be 64. That's 64 grams of oxygen. And this energy is if we have 2 of these, which would be 18 times 2 is 36. 36 grams. So those are all relationships that all mean the same thing. So, for example, here, how much heat is released when 4.5 grams of methane is burned at a constant pressure? Okay, so 4.5 grams, we're doing grams and methane. That's that guy. So it's going to be 4.5 grams. Get rid of grams and go to moles. I'm going to use this. The last time I went straight to moles, but this I'm going to do, I'll do both versions. So 4.5 grams, grams to moles, 1 mole gives me 890 kilojoules of energy. That's using this relationship with these moles. And then this is just 1 to 16. I also could do this, 4.5 grams, and use this relationship. 16 is to this. Dot line, get rid of grams, and go to moles. 890, 16 grams. Both of these, you'll see I get the same answer, and I'm sure you can calculate that on your own. Alright, now again, what happens if we change around things? Energy in equals energy out. So this case, when we flip this thing, when we flip a reaction, what happens? Our delta H goes from positive to negative and vice versa. Okay. So at this point, I flipped this thing, so it went from 890 negative to 800 to a positive 890. Now that's the amount of kilojoules to put, oh, we flip this thing, sorry. All we did with this thing is we doubled it. So this guy is for 1 mole to go through, now we're doing 2 moles. We'll get to the flip here in a second, the next one's flipped. So this is rather than 16, we're putting twice as much through, so it's 890 just times 2. And that number goes right there. I'm sure you can do that math on your own. Same thing here, we just happen to, it's not balanced. We need a 2 here, and we'll need a 2 right there. But it's flipped. So rather than having 890 in, it's 890 out. Rather than exothermic, it's endothermic. It's a positive 890. Alright, now I took this thing and I did cut everything in half. So rather than being 1 mole to go through for the delta H, I got a half a mole. So it's 890 divided by 2. And that's my new kilojoules per reaction. Okay. Next one up here. Alright, so we got some odds and ends here. Okay, so this is a good style question for calorimetry. Got a kind of reaction. In an experiment, student placed 50 milliliters of 1 molar HCl at that temperature in a coffee cup calorimeter. The solution was added 50 milliliters of 1 molar, also at that temperature, mixed them together, and we got 32 degrees was how much it warmed up to. The density of the final solution is 1.05. And again, as a little stipulation, this is what we got here. Okay. So let's take a few moments. Let's try and see what we got. How much energy was evolved? Okay. So Q equals mass times change in temperature times specific heat. We have 2 beakers. Now the biggest mistake here is that we have 2 beakers mixed together. Now we have a large beaker of stuff. Once it's mixed, is now 100 milliliters. 50 and 50. So now we have 100 milliliters, and the chemicals in there are reacting, and they are radiating to the solution, which is collecting it. So this is now, and you also need to add this in here. So it's a 1.05 grams per milliliter. Okay, so this just means that times 100 would be what? 105 grams. So this would add the whole thing up. So 105 grams. That's just that little bit because we're doing the total thing. Change in temperature is 32.2 minus 25.5, and that's my change in temperature. All right. .8 is my change in temperature. And then my specific heat is just they're saying star here, it's not changing, 4.18. This will give me my Q that my process, my chemical reaction evolves, and the water solution is absorbing. All right, so let's do this. All right, 105 times 6.8 times 4.18 equals 2984. All right, 2984. Okay, what's delta H for this reaction? Well, delta H is just Q per mole. Okay, now we want to make sure we can divide our moles by anything we want. We want to make sure the moles we divide by the mole are actually being used. So typically moles of a limiting reactant would be great. I don't know, it wouldn't matter if we have two things limiting, it wouldn't matter which one we use. So in this case, it would look like we have 1 molar, okay, and we have 50 milliliters of 1 molar is added to 50 milliliters of 1 molar. So the same concentrations, the same volume means equal moles. Okay. All right, so let's solve out the moles here quickly. All right, so molarity times moles equals liters. Molarity is 1. And I want to use the 50 milliliters because that's the amount of actual moles that I have for that half item. So 0.05 liters, and that's just going to be 0.05 moles. So it's going to be this guy, 2985 divided by 0.05 moles, and we're going to get our answer in joules. So divided by 0.05, and we're going to get about 59,690 joules, which is 59.6 kilojoules. All right, divide by 1,000 to get myself from joules to kilojoules, 59.6 kilojoules. And that's per reaction. Now, they don't ever put per reaction, but that's per cycle. That's what happens if I cycle 1 mole of this thing. All right, how about results change if 2 molar NaOH was used? And the answer is, well, it wouldn't, no change. Because then this would just be in excess, and the HCl would be limiting. Well, what would be the delta H for this reaction? Well, this we just did for 1 mole, now we're putting 2 moles through, so it would be this guy just times 2. All right, so good examples there. Methylhydrazine. All right, so we got CH6N2 is commonly used as a liquid rocket fuel. Okay, got to come from ration here. 4 grams of methylhydrazine is 4 grams of this. In a bomb calorimeter, temperature goes from 25 to that. In a separate capacitor. Okay, so there you go. What's the heat of a reaction for this when 1 mole goes through the calorimeter? What is the heat for the combustion when 1 mole goes through? A couple things you want to note here, okay? And what's the delta H? Take a minute, pause it, try it. Okay, a couple things I noticed right off the bat is this guy here. It's called heat capacity, okay? Well, look at what you get, kilojoules per degree Celsius. This thing has changed. Looks like 39.5, 39.5, minus 25 equals 14.5 equals 14.5 degrees Celsius. Get rid of degrees Celsius and go to kilojoules. 1 degree Celsius is 70.79 kilojoules. Alright, times 112.9 or about 113 kilojoules of energy. Now that is that's Q. That's how much we actually absorb. And it is for when we have 1 mole. Now this is for 4 grams to go through. Okay, so this is Q for when 4 grams go through. I want to know what it is when 1 mole goes through. So I'm going to take my 4 grams and I'll just take this energy and divide it by the grams per mole, grams per 1 mole. Okay, so there's 2 ways you could do this one. You could use a straight proportion if you wanted. I got, in this case, you need to know how much one of these guys weighs. So let's go ahead and do this. It's CH6N2. This is going to be 12, 6, and 28. So this thing weighs, okay, 12 plus 28 plus 6 equals 46. Okay. So 1 mole weighs 46. So you could say that, for example, 4 grams gave us 113. What would 46 grams give us? Okay. And at that point, you'd have your simple linear proportion. So 46 times 113 divided by 4 equals about 1,300. So we're estimating a little bit. 1,300 kilojoules. Okay. So, or you could just take your kilojoules per mole to figure the moles out and just divide them. Okay. And that might be another pretty common way people do that. Take your 4 grams, go to grams, go to moles. 1 mole is 46, convert them to moles, and then put that moles in the bottom here, and just divide them out, you get the same answer. This is kilojoules per 1 mole. Okay? Because 46 is 1 mole. Alright, and then delta H is just going to be this guy times 2. This guy times 2, which would be 2,600 kilojoules. And that's per loop for this process. Alright, 0.2 moles of 20 milliliters of barium nitrate is poured into and reacts with 25 milliliters of 0.4 molar ACl, creating solid barium chloride. We have a density here. There's the heat, to drop of that. What's the enthalpy? Alright, so let's write the reaction item first. It's barium nitrate, these 2, goes to, or plus, NaCl becomes barium chloride plus NaNO3. And I want to know what the delta H for this reaction is. That's the, if we balance it, we got to put a 2 here, 2 NAs, 2 was there, and our balance. That's the amount of energy when 1 mole of this goes through and then 2 moles of this goes through. Will give me delta H energy. So we're just going to do delta H equals Q, and then Q per mole. Now you want to divide out by the limiting reactant. Okay, so let's get our Q first. So Q is just going to tell us how much energy was the water substance collected. Q equals mass times change in temperature times the heat. The mass was the total mass of the whole solution. Now keep in mind we just mix these 2 solutions together, and they're telling us that the density is 1.05, so it's a little bit more than 1. We got 25 plus 20, okay, that's 45 milliliters, so 45 milliliters, get rid of milliliters and go to grams. 1 milliliter is 1.05 grams, alright, 45 times 1.05, 45 times 1.05 equals 47.25 grams. Okay. So this is about 47.2 grams. Change in temperature, 2.5 degrees, 4.18, and this will give me your joules of energy. I'm assuming that you can calculate that out. And finally, we'll find the moles. Now, in this case, it's 2-to-1 ratio. Who's the limiting? Or are they both limiting? We know that NaCl is being consumed twice as fast, so we need twice as much of it. I got 20 milliliters of 0.2, and I got 0.4. Okay, I got double the concentration of this guy, and I have more volume. So by doubling the concentration would give me the money to actually match it. So what I need to do is use this one. This is my limiting moles. So limiting reactant. There's some of this is going to go unused. There's going to be NaCl floating around. So my moles is molarity times liters equals moles. Molarity is 0.2. Liters is 0.02. Alright, and that's going to, I know you calculate that, and this goes in here, and then there you go. Now, because we're basing this on the barium nitrate, it's going to be the joules per 1 mole of barium nitrate. And that is what the reaction runs. So that will be my delta H. If this guy was my limiting, then I'd use the moles of NaCl, and when I divide it out, it would give me the energy per 1 mole of NaCl. That would have to be doubled then, because we're not running 1 mole, we're running 2 moles through. There we go. Thank you very much.